and double check, make sure it's streaming and the voice is good. Okay. All right. So we have the base 10 scientific notation parser, which is your homework, and I'm going to use the same starting point here. And save it to my temp folder, which means it's going to be gone by the time I reset the computer. There we go. All right, so this is your program, and the first thing I would do, which is actually part of the recommendation. Okay, it's not timed yet, that's why. That sound that we just heard, that's my Ring doorbell, seeing motion and telling me that there's some activity at my house. It's a doorbell that has a video camera and a motion sensor, but it hooks up to the cloud. So when it detects motion or somebody actually ring the doorbell, it will give me a ring, and then I can use my phone to actually look at a camera that is attached to the doorbell, and on top of that, it has a two-way audio channel. So if it's somebody who wants to sell me something, I can actually talk to that person and go like, I'm not interested. And that person will have no idea whether I'm actually doing it in the house or I'm here, away from my house. Well, that's technology. And that's why, in this class, I keep, telling you guys, technology is going faster and faster. It's advancing, in an increasing pace. So at some point, we're gonna get over that hill. We're gonna roll that ball over the hill, and then how it's gonna do things, down the hill, we have no control anymore. It becomes a runaway train. Okay. So the idea of using standard int stdint.h is so that I can refer to the maximum variables, and I can also refer to type names that guarantees a certain width for my values. So it is kind of important that Mantissa 10 is a 64-bit unsigned number. So this is the first thing I would do, is really just to change Mantissa 10 to a guaranteed 64-bit unsigned integer. Now, if you do it on, using GCC on most platforms or code blocks, you don't have to worry because, it is already by default 64-bit wide. But I don't, like to take chances. So this is the way that I guarantee that it is going to be 64-bit wide. Is that okay? All right. So the next thing we want to do is to do the parsing. So when you're doing parsing, you want to use a general strategy. Now, you might notice that PTR itself is not a const pointer. It's a pointer to something that is const, but it's not a const pointer. So you can actually change PTR. You can increment the pointer to move on to the next thing. So that's going to be my general strategy, is to use pointer itself so that I can keep track of, okay, what have I seen already? What am I processing at this point? Do I recognize it? If I do, move pointer to the next character. And we'll start with something to parse the sign, okay? Struct parser p parser. And if you like to do commenting, which is a good idea. So what this will do is to examine what PTR points to. If this is supposed to return an int in this case. If PTR points to a minus, return non-zero. If PTR, okay, there's one more thing, returns non-zero and advance PTR. If PTR, points to plus, advance pointer, because I recognize the plus sign, but there's no, but I want to return a 0. Okay. Otherwise, just return 0 without advancing the pointer. Is that okay? Does everybody understand what this function does? Okay. So we'll go ahead and implement this. So I will have a result of 0. So by default, result is 0 already. And we can do it in Several ways. One way to do it is to use a switch statement. So this is the part that is kind of important, is we are not switching based on PTR, but we are switching based on what PTR points to. Without the parentheses it would work as well, but the parentheses emphasize that we are dereferencing PTR as a member of the structure pointed to by P parser. So now we can go to case minus, and then we have case plus. Okay, break. Well, should I do a break here? Yeah, I'll do a break. Case plus, break, and then we always have a default, which means, what if I don't see a minus or a plus sign? That will go to the default case. And break is not necessary here, but I'm going to put one here anyway. So if I see a minus sign, I'm going to return a 0, which means return a non-zero, which means result gets something that is non-zero. 1 is non-zero enough, so I just return a 1. And then we also want to advance the pointer. You will see this code quite often in this particular program. Once again, the parentheses are not required. It will automatically increment PTR as a member instead of what it points to. But just want to emphasize that we are just incrementing the pointer itself. Alright, so this is the entire switch statement. Because if it is negative, a minus sign, I will return a 1. If not, result has a 0 to begin with as a default value, so I don't have to do a single thing other than advancing the pointer to the next character. If it is not a minus or plus sign, it is something that I do not recognize. But if I don't recognize, as a sign, it means the default sign of 0 should be returned. Okay, so now I just say return whatever result is, and that's my parse sign subroutine. Are there any questions about the parse sign subroutine? Are we okay so far with this? Okay. So the next thing I will do is to check and see whether it works or not. So that's the first thing I check, is to say parser, P parser points to sign just equals to parse sign, and then we are passing P parser as the argument to parse sign. Is that okay? So at this point, the program doesn't do much except it will attempt to recognize the sign. Is that okay? All right. Okay. So we'll save the file and compile the program. -G to include debug information. -O to specify the actual the name of the executable file. -1 all to turn on all the warnings. And I think that's all we need. Okay, no input file. Okay, of course I have to give it the program to compile. There we go. And it complains about, okay, there's a typo on line 21. So let's fix the typo on line 21. Parse, P-A-R, parser. Okay, there we go. Instead of just parse. Same thing here. Fix that. Okay. Recompile. Okay, so this warning you cannot really get rid of because we do have a label in main that has no particular use at this point. So it's time to debug the program. In other words, I'm going to go into GDB to test my program now. Parse sign. Put a breakpoint at label L1 in main. Run the program with a value. So I'm going to test it with 3 test cases. The first one is just 2. Okay, by the time I get to the breakpoint, what should be the sign of this particular scientific notation? Should be a 0. Because the sign only gets a value of non-zero when it is negative. Okay, so this should be 0, which is good. Okay, next I'm going to run it with +2. What do you think sign should be in this case? 0 or 1? Should be 0. Okay, because it is not negative. Anything that's not negative is going to be a 0. Anything that's negative is going to have a value of 1. Okay, that works. So now this is the last case. Okay, run it again, but use -2 to test it. Once again, we print out what is the sign, and it is 1. Okay, so far so good. Now the other thing that you also might want to check, okay, this is Optional, but you might want to check PTR, because you can see the PTR is no longer pointing to the negative sign. But that's good. That is exactly what we expected to do, because once it recognizes something and processes it, it should move the pointer to the next available character. Is that okay? All right, okay. So now I feel confident enough to go back to my code and add some additional thing. And you will see me testing the program like this multiple times, okay? Because every time I add something, I want to test it. Every time I add something, I want to test it again. When you're doing it this way, not only are you kind of practicing the GDB commands and stuff like that, you're also making smaller steps. And the key of making smaller steps is if one step is, introducing a new bug into your code that is otherwise working, you can easily figure out what change is breaking your program. Okay. All right. So the next parser is going to parse an unsigned number. So I just say parse unsigned, and it's a struct. I'm going to pass the same kind of parameter, except this one also has an initial value. The initial value is going to be a uint 64 underscore t, and I'll just call it initial value. And this one is going to return an uint 64 underscore t as a result. Okay. So we'll deal with the logic first, the control structure, and then we'll deal with, okay, so what do we do with all of these digits? An unsigned number needs to start with a digit, okay? So I need to say, as long as I am seeing a digit, as long as PTR is pointing to a digit, I got something to process. So we'll say, as long as whatever parser PTR points to, parser PTR, if it points to something that is less than or equal to the ASCII code of 9, and that very same thing is greater than or equal to the ASCII code of 0, then I want to stay in the loop. Okay, I need an extra pair of parentheses on the outside, like so. Then I got something to process. First thing that I need to remember to do is to say, let's increment the pointer because it is processed already. So at this point, I'm only emphasizing on the control structure, but not so much, I cannot do this until I have processed it, okay? But this is the general structure, is if I see a digit, I'm gonna process it, I'm gonna move the pointer to the next thing, I go back and see if I'm seeing another digit. So I keep doing this until I'm all done. Is that okay so far with this general logic, general strategy?
I think you're missing an asterisk for the passing struct. Are we passing a parser?
On which line? Let me turn on line numbers so you can refer to. Which line are we talking 32. About? Line 32?
Will we pass
Oh, you're right. Yep, we're missing the asterisk here. Thank you. All right. So now that this is the overall logic, we can test it first, okay? We can test to see whether this works. So once again, I'm testing a program that is known not to be complete, not even close, and here we go. We got some control reaches end of non-void function because it's supposed to return a unsigned integer. So over here with parse unsigned, I'm just gonna say return initial value, and I need to call it too. I forgot about that part too. So we say parser Mantissa 10 equals to parse unsigned with parser as a pointer to the structure and also an initial value of 0. Okay, so we'll go ahead and run this, compile and test this program again. Okay, so we GDB the whole thing again and set up a breakpoint, main L1, and we're going to run this program this time with something that's funky. Okay, so we'll say let's try -5 ABC. Okay, well, it will still tell me whether the code works or not. Okay, so let me run it. At this time I can print all the certain members of the parser structure, but what should I be seeing? The first one is the sign, right? So we say, what is the sign? What do you think it should be? The test string should be a 1. Okay, very good. If I say print p.ptr, where do you think it should be? I'm calling parse unsigned, okay? So where do you think ptr should be pointing to at this point? Should it be pointing at the 5, or should it be pointing at the A? The A, okay? And that's exactly where it's pointing to, which is good because it means that it knows when to terminate the loop. Okay? I'm not doing a single thing. I'm not interpreting the digits yet, but I got the right control structure to know when to get out of that loop. I will keep processing digits until I'm done. Okay, let's run it one more time. And this time we have, a whole bunch of digits. Okay? And the sign would be the same. Okay, that's not surprising. But what about PTR? Where should it be pointing to with this example? It should have processed all of these, and we should once again stop with ABC. All right. So I confirmed that the control structure of parse unsigned is working. Okay, that's important. Now we can go back and go to parse unsigned and say, okay, before we increment the pointer, we better do something with it, right? So when we do something with it, and the return value is initial value, that means initial value, we need to multiply whatever it is by 10 because we have seen the more significant digits already. So the new digit becomes the new least significant digit. And all the digits that I have seen become one digit more significant than what they were before. So now we say initial value times 10 plus whatever the value of the digit is. Well, we already know this is a digit from 0 to 9, because otherwise I wouldn't be in the loop itself. I would have exited loop. So that means the actual value is whatever p parser ptr points to minus the ASCII code of 0. I don't even need to know the actual code of 0, okay? Because whatever it is, I just need to subtract that amount from the ASCII code of the character pointed to by ptr. Are we doing okay so far with this code here? Okay, you can separate it into 2 lines if you want to. In other words, you can use the first line to multiply initial value by 10, and then on the second line you add the value of the digit the ptr is pointing to. That works as well. I'm just combining those 2 operations into one. Are we doing okay so far with this code? Is that okay? All right. Okay. So if this is okay, I'm going to exit the code. I will give you this entire file also, so there's no need to. It's also being recorded, so so there's no need to try to copy as quickly as you can. So I'm going to rerun this code. Okay, compile again, and rerun this code. And this time, same thing. Set up the breakpoint first. So this time I'm going to run it with something like that, and then an ABC. Okay. So this time is different because Mantissa 10 should have the value of 203948098. Okay. So I run the code. The sign should still be 1 because it is a negative quantity, but then the Mantissa should now be the 2039, the huge value, and that works. So that means I am parsing and I'm interpreting the digits correctly, which is good. But I still want to make sure that PTR is not messed up, because every time I make any changes to the program, I could have introduced a bug. So it is always a good idea. It doesn't take long, right? But it is a good idea to confirm that it is still working. Is that okay? All right. So now we go back to the main code again. And then we say, now that we have the ability to parse assigned and the ability to parse unsigned, let's see how we can do it here. We know the first part is assigned, so this has to be here. I have to try and see if there's a sign that is processed. This will take care of everything to the left of the decimal point. It will stop either at the decimal point at an E, or at a null character. Those are the three proper ways to end a string, but it can also be anything else. It can stop at any other place. But at this point, I know that I need to check for the period to handle the decimal point and everything to the right of the decimal point. So I'm not going to make a new subroutine to do this part. You can make a new subroutine to do it if you want to, but I'm not going to do it. I just need to say, okay, are we pointing to a decimal point at this point? If so, I got something to do. So this is the optional part corresponding to the regular expression, because everything from the point and then a whole bunch of optional decimal digits, that's optional, and that's what this conditional statement is going to process. Is that okay? All right. So the first thing we do is to say, okay, now that we have seen the period, let's move on to the next let's move on to the next character. There is no processing to do with the decimal point, because the whole purpose of the decimal point is to separate the non-negative powers of a number from the negative powers of that number. So there's really nothing to do here. However, I also want to this is a trick that many people may not know, okay, which is okay, because I have done programming for many more decades than you guys. So it's okay to have to not know every single trick available. So what I'm doing here is to take a snapshot of the pointer at this point. Okay, maybe not at this point. I need to do it after I advance the pointer. So I'm gonna do that, and there we go. Okay, so I'm remembering, I'm taking a snapshot of the pointer right past the decimal point. Okay, because there's a reason I need to do this. And then what I'll do is I'm gonna do parser Mantissa 10 equals to parse unsigned p parser, but this time I'm not going to give it a 0, because this time I'm going to give it p parser Mantissa 10 again. In other words, I'm treating all the digits to the right hand side of the decimal point as if they are just extensions to the other digits of the mantissa. It is as if the decimal point is not there. Okay. I know there are other things to adjust, but I need to make sure that this part works also. Okay, so I need to double check first before I move forward. Now there are people who like to do this. Okay, and I think it's a great idea, is to use a to-do to remind yourself, what else am I supposed to do at this point? Okay, so I need to adjust exp10 according to the number of digits to the right of the decimal point. In other words, I'm leaving a note to myself as I test the program up to this point to say, okay, after you're done with testing this part, this is what I need to do next. A lot of syntax highlighting editors will actually highlight to do just like this, just so that it stands out, so that you know that, okay, this is something that we need to do. I think fix me is the same way. Let me see, fix me. Yep, fix me is also the same, because it stands out, so that every time you use fix me in comments, it really stands out to remind you, okay, this is something that I need to do. Is that okay? So some of this does not relate to cisp310 per se, but it relates to programming in general. Just little tips that I find useful for my own programming. Alright, so let's compile the program again, and this time it complains that OPTR is set but not used. Okay, that's okay. Okay, it doesn't, because we have not changed it yet. We don't have a need to use it yet. So we'll set up a breakpoint. Oops. Okay. L1. There we go. So we run the program again. If you need to delete a breakpoint in GDB, you just do a D and then the number of the breakpoint. So I want to delete breakpoint number 1, so I say D1, and that breakpoint is now gone. I run the program again. Okay, this time I need to supply a decimal point and an ABC here. So the program, if it does work correctly, I might have too many digits. I'm gonna reduce the number of digits here. So if the program does work correctly, it will give me 2048093203 as my Mantissa 10, and PTR should stop at the A again. Okay, that's my expected behavior. I haven't done a single thing to EXP10, so it should still be 0. So I run the code, I print. If you want to be lazy, you can just say print P, that will print all the members as well. So if we look at all the members, PTR is pointing to ABC, that's good. Sign is 1, that's good because this number starts with a negative symbol. And then Mantissa 10 is exactly what I expected, which is 204809823203. So everything works up to this point. And you can see how I'm taking really, really baby steps. Okay, you code a little bit, test it again, code a little bit, test it again. Okay, go back to this code, go back to the to-do. So now I'm going to implement the to-do. So now the question is, how do I know how many digits are to the right of the decimal point? Yep.
You can create a local variable that counts it.
Well, it's already counted. I have old PTR for a reason.
Oh.
Okay, so P parser points to PTR. This is the new pointer. This is already adjusted. In other words, this is right after parsing all the digits to the right hand side of the decimal point, right? So if I subtract OPTR from this, what do I get? Well, hold on a second here. Can we subtract pointers? Did you guys learn about pointer arithmetics in CISP360?
It was covered.
It was covered? Okay.
Like, very briefly.
Okay, as it turns out, it's a very useful feature in some type of programming like this. Okay, so in this case, you're given 2 pointers, which are basically 2 addresses in memory, right? Now the question is, what is it going to give you, the difference? Is it going to give you the number of bytes in between, or is it going to give you the number of items in between? If it's number of bytes, then it is dependent. It would not be dependent on the type of the pointer, because it's just telling you, oh, we got 512 bytes between this point and this point. If it is telling you the number of items in between, then it depends on the type of the pointer. Because if what you're pointing to is 8 bytes wide, then it will say, oh, in terms of bytes, it's 512, but in terms of the number of items, it's 512 divided by 8. Okay? So the answer is the letter. In other words, in C, when you subtract pointers, it gives you the number of items in between, not the number of bytes in between. But since we have character pointers, and each character is 1 byte, so in this case, it is both. It is telling you the number of bytes in between, but that's only because 1 char is 1 byte. Okay? All right. But that's useful, because this tells me how many digits we have to the right-hand side of the decimal point. So I need to do something like this now. I can say exp10 minus equal to that amount. Because the subtraction is always going to give you something that is non-negative. It can be 0, but it's non-negative. So you need to decrease exp10 by that much in order to compensate the implicit shift of the decimal point to the right-hand side. Is that okay? All right. So let's check it. Okay. Every time we make a change, we want to double check and make sure that it is still working. So we go back to GCC. Oh, okay. We need to fix it. exp10 is not a variable; it is a member. So we have to kind of fix that. P parser points to. And by the way, do you also know that this is the same thing as dereferencing the pointer first and then addressing a member? So these 2 statements are the same. Is that okay? Because C gives you several notations, several ways to express the same thing. On the first line, let me turn on the line numbers. On line 58, that's the usual way that people express I need to access a member of a structure that is pointed to by a pointer. Okay. On line 59 is the more kind of spelled out way to do the same thing, because the p parser is a pointer to a structure. So when you dereference it, okay, let me highlight the parentheses here. This gives you a structure. What can you do with a structure or an object? Well, you can access a member. So that's what a dot is. So these two notations are expressing the same thing. For convenience, we use line 58. But line 59 spells out the operation in, just more exactly. So you can use either one. All right, so we're going to test the code again. Compile, no errors this time. That's good. And then GDB, set up a breakpoint, run the program with. Now this time I want it to be a little bit more specific. So we'll have 2.000. So this time Mantissa 10 should be 2000, and then exp10 or exponent 10 should be -3. So we run the code, we print p. Yep, that works out. Mantissa 10 is 2000, exp10 is -3, and it makes sense because this is the value of -2 really is 2000 times 10 to the power of -3. So I have preserved the value. All right. So next we need to handle the exponent, okay, which is also optional. So every time you handle anything that is optional, you would use a conditional statement, and you say, do we know whether we have a e component or exponent component here? So we do a simple character comparison. If it does match, the first thing we do is we advance the pointer so that we say, yep, that e is handled, because the e doesn't do a single thing other than indicating that we do have an exponent component. So now we are getting to the sign, the optional sign of the exponent. So it can be there, may not be there. So this is where we need some local variables. So we can say this is the exp sign. We need a local variable for that. And we also need another local variable for exponent 10, exp10. It's okay to use a local variable that has the same name as a member. There's no way these two can be confused. Why not? If you look at this from the perspective of the compiler, can the compiler confuse the local variable exp10 with the member exp10 of the structure? Nope. Because as a member, it is always to the right-hand side of a dot or a pointer notation. As a local variable, it doesn't go into those places. So there's no way it can be confused. Okay, so that's good. So now we can say exp sign is parse sign, and then we pass p parser as a pointer to that thing, and then we can say exp10 equals to parse unsigned p parser again, and this time the initial value is going to be 0, not the current value of exp10 member of the parser structure. Okay, that is important because we'll do the adjustment later. So when this is all done, then we can do all the adjustment. We can now say that the exp10 member of what p parser points to is going to be offset by exp sign. If it is a 1, then the number is negative. Otherwise, the number is non-negative times the actual absolute value of the exponent. Okay, so let's take a look at this code. Are there any questions about this chunk of code from line 60 to line 68? Okay. Are we seeing the first char of the exponent? Okay. If the answer is yes, okay, move past the e of the exponent parse the optional sign, parse the exponent value, and then we adjust the EXP10. Are we doing okay so far with this code, or are there any questions? Because if you have questions, now would be a good time to ask. It's all good? All right, so let's give it a spin. Okay, same error, same warning, which is okay. We know that one is going to be there. Put a breakpoint at main at 1, and then we run the program with -2.345 with E. Okay, let's make it +5. Okay. So when you run the code, it will stop at the breakpoint, hopefully, because if you have an infinite loop or somewhere, it's not going to get to the breakpoint. But before we do the print, we want to figure out what should be each member of the structure doing. Okay, PTR should now be pointed to a null character, so it would display it is as if it is an empty string. Mantissa should be 2345 or 2345. EXP10 should be 5 minus 3. The -3 comes from the fact that we have to shift the decimal point 3 times in order for the mantissa to be an integer. So 5 minus 3 is 2, so we are expecting EXP10, the member EXP10, to be 2 at this point. And then we check everything. Sign is 1, that's good because we do have a negative sign here. Mantissa 10 is 2, 3, 4, 5, that is good. And EXP10 is 2, that is good as well. So far it's working. And let's try it one more time. So we'll run it with positive 2.000 E minus 5. Okay. So this time the exponent should be -8 because -5 minus 3 is -8. Mantissa 10 should be 2000, and then the sign should be 0. Sign is 0, Mantissa 10 is 2000, and EXP10 is -8. So everything is working so far. Okay. So the next section is kind of really optional. When it's not only for this class, but also for any class that requires you to write programs, and the program is kind of difficult and it will take you some time to write it, is how do you keep testing your code time after time, as you are trying to debug your code. You can do it manually. You can write down, on a piece of paper, all the test cases that you think are important. Okay, that's one way to do it. But you can also automate that process if you're using GDB on the command line. So what I'll do is I'm going to write down a test script here to test my program. Everything that I type in this file can be fed to GDB as if I'm just typing it interactively. So the first thing I do is I set up a breakpoint, just like before, and then I run the program with a particular value. So let's say we're just testing it with 2. And then what we can do next is, remember, this is as if you're typing the code. So by the time you are done with the run, it would have reached the breakpoint already. So now you can actually you can do this. You can do a pp, which is print p, which means it will appear in the log. Let's just try this much first, okay? So when you run GDB like this, you can say GDB parse sci, and then you can use the redirect symbol to redirect the file into GDB. So this way it is almost as if you type everything in the file when you're in GDB. So when we run the code, okay, it looks kind of confusing because it generates a lot of gibberish. So all of this stuff here is just gibberish. But this line here is indicating that we just set up a breakpoint on line 79 of the program. This line here indicates that we have reached the breakpoint. Okay, and this line here is the print statement, is the PP, because print can be abbreviated to just P. So it is printing that we have 0 for the sign, 2 for the mantissa, and 0 for EXP10. Is that okay? All right. But this way of doing things is not ideal either, because I still have to kind of manually go through to check to see if everything is right. So the shortcut to do this is you use a condition. So I would say that p dot sign should be a 0, p dot mantissa 10 should be 2, and p dot exp 10 should be a 0. So I have one gigantic condition here, but to make this output easier to interpret, we can now say if that is true, print the string of 2 works. Okay. Otherwise, we print the string of 2 failed. Okay. Tense consistency. Okay, so what this is going to do, okay, let me run the code again, is it will give you some output like this, and it will make a conclusion and just say that 2 worked. So if you make a mistake, it will just say 2 failed. You don't have to interpret every single time. Now this doesn't seem to make that big of a difference, but when you have more test cases, then it will start to make sense. So let's say this is 2.000, okay? So Mantissa this time would be 2000, and your exponent should be -3 this time. And of course, we really should change that to 2.000. There we go. Is that making any sense? And then you can make more fancy ones. Okay, add a sign. So this time the only difference is the sign should be a 1 instead of a 0. Or better yet, you just compare to see whether it is non-zero. That would be a better way to do it. And also update the strings so that when it prints the correct one. So we have to fix this one too. This is 2.000. There we go. Is that okay? And and you can extend this, as much as you want to. You can say, okay, now we want to add exponent, okay, with no explicit sign. So let's do it E3. So in this case, you want the exponent to be exactly 0 because it cancels out. Okay. I mean, it would be exactly the same as the one before, right? And let's see, make it a -3. So this time the exponent should be -6. And I forgot to fix all the strings, so now I need to go back and fix all the strings. This is E3. Oh, there are 2 of those. E3. But this is really just to make the output more legible, so that you don't have to spend a lot of time looking at the output and go like, okay, which one failed, which one worked again. This just makes it easier. There we go. Let's try again. So now you can see for each one, it will say whether it worked or not. So it says, this worked, this worked, this worked, and so on. But there's still a lot of gibberish in between. So if I were to look at this and go like, I really want to streamline this even more, now we can do this. Now this is definitely way out of the scope of this class, but it is useful techniques to learn, okay? You can use the program called grep. Grep stands for, it's a program that will filter a text file or whatever you feed into it, and it will only print the lines that contain a certain regular expression that you have specified, okay? So you can specify the regular expression. In this case, you can specify alternatives. You can say worked is an alternative, and then you have to use / vertical bar as a separator from the alternative. The alternative is failed. So now you're saying, filter out every single line from the input except for the ones that contain the pattern worked or failed. Okay. So if I look at this entire line, this is the first command. We know this one already. But instead of printing the output to the console directly, the pipe symbol is saying the output of the first command is going to become the input of the second command. Okay? So now when we combine these two commands and press the enter key, it filters out everything. It just says, okay, what worked and what failed. Now let's break the program. Let me break the program a little bit so they can also display the failed messages. So, well, you can also tweak GDB, but I'm going to break the program. So we'll break the program by using the wrong multiplication to adjust for the sign of the exponent. In other words, right here, let's just say that I have a typo and I use negative negative both times. So that's going to break some of the program, some of the code, but not all of the code. Okay. Recompile the program first, and then rerun the program. And you can see this time, any positive exponent that are stated explicitly failed, which is expected because I just added negative symbol where it's not supposed to go. But you can also see how this is really handy, because every time you found a test case that is really useful, that can help you debug some of the code, you just add it to the whole script, which is good for regression test, which basically means that you are retesting every single time everything that is known up to this point to be useful as test cases. So now I fixed the program. I go back and recompile and rerun the GDB, and now we confirm that everything worked. Is that okay? Now, if you know that certain things are guaranteed to work, you're not concerned about it, you can just take out the alternative and just say, I'm just looking for the cases that it failed. So that will help you simplify the output, and so you can only focus on the stuff that is not working. Is that okay? How many of you still have other programming classes to take, like 430 or 400? Okay, so you might want to consider something like this, to help you debug your other programs. It takes a little bit of getting used to, because I know many of you use code blocks or some kind of GUI to write your program, which is great. I don't know how to use code blocks. It has 20 gazillion options, and to find out how to do something, you have to go through the menus and submenus and whatnot. But doing it on the command line, using the command line, gives you options that are really kind of convenient in the long run. It will take you some time to learn how to do this, but once you get into it, once you figure out the command lines to do something, once you figure out how to use GDB, the command line version of GDB is much more than the GUI, what the GUI is going to expose. Code blocks is really just an editor and what we call IDE, or Integrated Development Environment, that is sitting on top of GCC and GDB. So down below, it is still using GDB to do everything that you have to do in debugging your program. So is that okay? All right. So your next homework assignment is to take the output of this program and continue with this one. So in addition to parsing, now you need to do the conversion. Okay, I got this working with the other class already, so I'm going to add the code here. So at this point, after the parsing, you need to do the conversion. So to do the conversion, we'll have a uint64_t d as a variable. So now we say d equals to convert to double, and then I'm just gonna pass the entire structure in. All right. So this is the interface of convert to double. Is you take the finished product in parser, the structure, which will include the sign, the Mantissa 10, and the exponent 10. And then you go through my notes, you figure out how to convert that value so that it will now be represented as a double precision format. Do you guys understand the general idea of what I'm talking about, what the program is supposed to do? So now we need to add one more function here. We can say, uint 64 underscore t convert to double struct parser p, and I'll give you some extra code here. We'll say, uint 64 underscore t result equals to 0 and return result. Insert the code to convert base 10 scientific notation to IEEE double precision floating point, but stored in 64-bit integer. You cannot use any double type in this code, because otherwise it's just a pretty easy homework assignment. You can just cast. You can cast and call some math functions, and you're done with it. So instead of doing that, I want you to use the use the techniques in the notes to perform this conversion. Okay, so which part are we talking about? We are talking about mostly in section 5 of the floating point number representation note. So when you look into this note here, section 4 is talking about the base 10 representation, the scientific notation. We are done with that. Section 5 is the conversion. So you want to use the section 5 to get to it. Section 5.1 is already done. Okay, that's part of your homework assignment that was due today. So you're really starting with 5.2, okay, which is a general description of the strategy. How are we going to get rid of the exponent of 10? So you have two ways to proceed, depending on whether exp10 is less than 0. If it is so, you use this logic. If exp10 is greater than 0 to begin with, then you use 5.2.2. Is that okay? Each one, okay, is a double loop, because this entire thing, there's an overall loop on top of these two steps to perform these two steps as long as E10 is less than 0. E10 in this description is exp10 as a member of the parser structure. Okay? This is a loop itself. This is an inner loop. These two steps are just the regular steps. They are not a loop. But together, when you look at this entire thing, this is the inside of an outer loop. The outer loop will continue to run as long as exp10 continues to be less than 0. So you can see there's an outer loop, and then there's an inner loop, followed by two statements that are not in the loop. Is that okay? What about these individual steps? How do we find out whether m, which is the mantissa, is less than or equal to the largest numerator value plus 5 divided by 2? The numerator is your m, is the mantissa. Okay? And what type is the mantissa again? It's a uint64, which means it is an unsigned 64-bit number. How do you know what is the largest 64-bit number unsigned can be? And you want to divide plus 5 divided by 2. Go ahead.
Is it a 32-bit number?
It's a 64-bit number. Yep, it's a 64-bit number, but the tricky part is you have the plus 5 and then divided by 2. But instead of doing the plus 5 and then divided by 2, what is the other way to do it?
Divide by 2 afterwards.
Divided by 2 and then just add 3 to it. Well, sort of. Is that okay? It doesn't really have to be absolutely the largest, it just has to be getting up there. Okay, but I'm just telling you that if you add 5 to the largest numerical value, it's going to overflow, it becomes a very small number again. So do not do that, that won't work. Do you guys understand what I'm talking about? Because the largest numerical value is already all ones using 64 bits. You add 5 to it, it's going to overflow and then become a very small number, 4 to be exact. Okay, so that's not going to work. So you will have to divide it by 2 first, and then add just a little bit to it. Okay, so you want to keep this loop until this condition is no longer true. What about this step here? Do we know how to do this in C and C++? Okay, I'm just magnifying here. Do we really need to use the floor function? Okay, let me highlight the part that I'm talking about here. We know that M is a 64-bit unsigned value. So to perform this step, which is the highlighted portion, what do? There's a division involved here, because of the fraction, but there's also a floor function, which gives you the largest integer that is less than or equal to whatever it is enclosing. But do you need that in your homework assignment? No, because integer division automatically does that. But you have to do the plus 5. Okay, do you guys remember in our discussion why we are adding 5 before we divide by 10? What happens when we don't do that? Oh, you guys do not remember.
The average, right?
It has to do with bias. If you don't add 5 before you divide it by 10, then every single time you perform this step, the actual value, the value returned is going to be smaller than what it is supposed to be. So if you repeat doing this many times, then your actual result would be significantly smaller than what it is supposed to be. So this is a problem of a bias, which means every single time you run out of digits, every time you truncate, you're always erring on the smaller side. By using the plus 5 and then divided by 10, you are actually doing rounding. So rounding is losing precision too, but it is not biased. Sometimes it's bigger, other times it's smaller, 50-50 chance. So you don't have, you're not always erring to one side, so that your actual value will now be all the way to the other side. Okay? All right. So if your exponent 10 is more than 0, then you perform basically the same thing, and once again you have to figure out how to express the largest integer divided by 10. Okay? There's a symbol. Okay? I'll give you a clue. You want to look up the documentation of sddint.h. Just type it in Google. Great. It thinks it's a URL. Okay, there we go. So you look up here, and it contains a lot of definitions. So it contains the type defs of all the individual types. And then it contains something that is going to be useful, limits. And you read a little bit more until you get this. What is n again? What do you think n is? Yep, n is the width of the number in number of bits. So n is supposed to be 64 in your program. So you have all of these things predefined. You don't have to figure them out. You just use the predefined macros in your program. Is that okay? Right. So moving on, do we know how to normalize the Mantissa? In other words, can we implement this as a loop? Can we implement this as a loop? Yep, we should be able to. right? Okay. Once again, we have rounding issues here. Okay, so we're just using rounding instead of truncation. And I think the rest are pretty easy, except all the way to the bottom here. Bitwise OR and bit shifting can be useful. Do we know how to use bit shifting? The less than operator. Okay, so that will place the components to the right bit position, and then you use a bitwise OR to combine all the components together. All right, so that's basically what you need to do. I think the complexity of this code is actually less than the parser. It's not as tedious, but there's a little bit more math involved in this process. All right, so if you have any questions, now would be a good time to ask, because if not, I'm going to upload the parsing.c to Canvas, and you can use that as a starting point. But before I do that, I'm going to compile and make sure that I don't make some stupid mistake somewhere. Okay, that's not a stupid mistake, because D is existing only for the purpose of testing the code, but the scope of D is at the wrong place, because I need to pull D out here, because otherwise D does not exist by the time we get to L1, which is where I will test your code. Okay, so I need to upload this code to that particular module, and that becomes your starting point. So I'm going to add a file. Alright, so you should be able to download parse-1.c, which is the starting point of this homework assignment to convert to double. Any questions before I stop streaming? Any questions? Alright, so I'm going to stop the streaming.